coordinate setup, we need to find the area of a given curve for the first quadrant. We know the first quadrant is from 0 to pi by 2, so we're clear about that. But how do we integrate? A small sort of a description of how we do it is by dividing the polar curve into small d theta elements, okay, and integrating it over d theta elements. But you cannot integrate it simply as r, because this looks like an arc. Individually, each one of them looks like an arc. So the formula is like the formula of the arc length, which is half r squared theta. Now you must understand that r here is a function of theta. So the integration is over r, is over. So in this case, we can set up the integral pretty easily. So for the first quadrant, we need pi by 2, and we see that this sort of a chordoid is a very simple shape. There's no the first quadrant means the first quadrant, right? Because as you go from 0 to pi by 2, the graph would be formed in the first quadrant. For instance, if r was negative with respect to theta, it would have formed in the third quadrant. So we have to be careful about what they're asking. So they're asking for us, from us, to give them the area in the first quadrant. We should respect the symmetries of the curve. Now, r is 1 plus sine theta. It should be squared and it should be integrated. So it's pretty simple now. So we have three terms actually. One, I'll just write it immediately. Sine square theta plus 2 sine theta. You know, this term and this term, they're easy, because you know sine theta integral is minus cosine theta, or sorry, cosine theta minus cosine theta. So you have to be sort of it's easier to do than it looks like. For the second term, sine square theta is a little difficult, but what you can do is just use the double angle identity. It's pretty simple. Okay, so you use this on this one, and the final result you should get is something like this. So this should be the integral.